So hello, my name is Florence Hudson. I'm Executive Director of the Northeast Big Data Innovation Hub at Columbia University. And I'm joined today by Emily Rothenberg, who just got us started, who also works at the Hub, and with Faru Garamani, who she and I are on the steering committee for the Ecosystem for Research Networking, as well as Maureen Dougherty from ERN. And we're delighted to be hosting our first quantum webinar series, co-hosted by the Northeast Big Data Hub and the Ecosystem for Research Networking with Dr. Monica VanDieren from NVIDIA. And Monica will be presenting Preparing Students for Accelerated Quantum Supercomputing. So whether you're a faculty, a researcher, or a student, or maybe a future student who wants to learn about quantum that's been in the world of business for a while in technology, this has many aspects I think you all can benefit from. Next slide, please. First, we want to mention the code of conduct for all the events that we do, hosted by the Northeast Big Data Innovation Hub. Basically, be respectful, and if there are any questions about that, we can put the link to the code of conduct in the chat. Next slide, please. So our moderators today, myself, as Executive Director of the Northeast Big Data Innovation Hub and founder of our National Student Data Corps. The Hub has over 24,000 members around the country and in some places around the world. And the National Student Data Corps has over 18,000 members, many educators and students that leverage open online free data science education, like what we're talking about today, related to quantum. I'm also PI for the COVID Information Commons, which is another NSF-funded grant, and we're in the Data Science Institute at Columbia. And I'm also on the steering committee with Faru for the Ecosystem for Research Networking. Emily is our program manager at the Northeast Big Data Innovation Hub for the National Student Data Corps. She has actually led the growth of the NSDC from maybe about 1,000 people to over 18,000 over the last few years that she's been here. And she's with me in the Data Science Institute at Columbia University in New York. And then Faru, who is a very close partner of the Northeast Big Data Hub, and she is Assistant Vice President for Research and Innovation at EDGE. On the ERN Steering Committee and on the Northeast Big Data Hub Steering Committee. So you'll be hearing from all of us today as we moderate this session. And now we want to jump into why you're here. And we're delighted to have Monica VanDieren with us today to talk about preparing students for accelerated quantum supercomputing. How exciting that we're at this pivot point in technology. So as a senior technical marketing engineer at NVIDIA, Dr. Monica VanDieren specializes in quantum and high-performance computing, driving the CUDA-Q Academic Initiative. Before joining NVIDIA, Monica contributed to IBM's Quantum Accelerator program. With a Ph.D. in mathematical sciences from Carnegie Mellon University, she brings over 20 years of academic experience at universities such as Stanford, the University of Michigan, and Robert Morris University to her work. So we are honored and delighted to have her with us today. And so now I would like to hand it over to Monica.
Well, happy Friday, everyone. I'm so glad that you could join us today, and a big thank you to the organizers at the Northeast Big Data Hub and ERN for putting the series together. The world of quantum, it's moving incredibly fast, and it's kind of hard to keep up. But today my goal is to answer 3 questions. First, what is an accelerated quantum supercomputer, and why is AI the secret ingredient that makes that so powerful? Then we'll move on to after we know what the technology is all about, we'll move on to the question about how we can fundamentally rethink our educational approach to prepare the talent that we need. And finally, I'll let you know where you can go from here. I'll make sure you leave with some of the resources to continue your learning and your teaching if you're one of the professors out there teaching quantum computing. Okay, so let's get started. Since the audience today is actually pretty diverse from a mix of backgrounds, I want to make sure that this is valuable for everybody. So I'm actually going to start with a very quick high-level overview of what we mean when we say quantum computing. We won't get lost in the weeds, I promise, but after that, we will be able to explore how to prepare students for the future of quantum computing if we first have a shared understanding of what we actually are talking about. So what is a quantum computer? Let's break that down with a little minute or two description here. The first thing to think about is how a computer works, it needs to store information and ultimately manipulate that information. And so your computers that you're familiar with, your cell phone, your laptop, your digital devices, they all use bits to store and manipulate information. They're basically like tiny little switches that are either a 0 or a 1, an on or an off. That's pretty much as simple as it gets. But quantum computers, on the other hand, use qubits to represent information. And the information is stored in a quantum state, and that can be thought of as a combination of like a probability and a phase. We won't get into the details of what that is for now, if this is new to you. But in the meantime, if this is new to you, you can think of it, a qubit, as just having a probability of being measured 0 or 1. Phase is also important, but like I said, we're not going to get into the weeds about that. So the idea is that with a qubit, you might have a qubit, like the first image here, that 100% of the time when we measure it, we're going to get a 0 and then, or an up switch. And then this other qubit might be in a state in which 100% of the time when we measure it, we'll get a 1. So they look very much like bits do. But qubits also have the possibility of having different probabilities of being measured as a 0 or a 1. So for instance, we might have a qubit that half of the time we measure it, we'll get a 0, and the other half of the time we measure that, we might get a 1. This is the concept that's known as superposition. There's way more to qubits that make them powerful, like entanglement and interference, but we don't have time to get into all of that right now. So those are the bits and qubit. And so one might ask, what are bits and qubits made out of? That was just an abstract idea. Bits are physically built up as transistors in your phone or your laptop. But for quantum computers, we're still in the early days of figuring out how to actually realize them physically. And there's a race to find the best way to build a qubit. It could be trapped ions, superconducting transmon qubits, or something entirely different. We're not really sure right now who the winner is going to be. In fact, the future actually might contain several winners in which there's a mix match of different types of qubits that might be good for different jobs. So we've seen the unique way a quantum computer might process information with qubits. So now let's talk about how this capability unlocks a new era of computational science by allowing quantum and classical processors to tackle some of the biggest problems that we face today together, each leveraging its own strengths. So for decades, we've made incredible progress using classical computers, especially with GPUs accelerating scientific discovery in the last couple decades. But there are fundamental questions in science and industry that even our most powerful supercomputers struggle to answer. So take chemistry, for example. Drugs or fertilizers or better EVs, these all come down to understanding how molecules behave. And a quantum computer actually could help us simulate this with an accuracy that's impossible with today's classical computers. And that could drastically speed up innovation in these areas. Similarly, in other fields like logistics or finance, finding the best answer to a complex optimization problem, it's a massive challenge. And quantum computing offers a fundamentally new approach to these solutions. And And so those are just some examples of why quantum computing is getting a lot of attention now. It has the potential really to unlock some problems we weren't able to solve in the past. And so, but this is the important thing to think about here is that the future of these applications is going to be hybrid. The quantum computers aren't going to be working on isolation on these problems, but they are going to be working in tandem with classical ones. But we're not at the point of solving problems that that classical computers can't solve yet, because today our physical qubits, the quantum computers that we're creating right now, are very noisy. The best quantum processors that we have today can only perform hundreds of operations on a limited number of qubits before the qubits themselves, the fundamental unit of information and computation there, becomes overwhelmed by the noise, and that's going to corrupt the computation. So it turns out that the partnership between quantum and classical computers isn't just for making scientific breakthroughs like in the last slide, but we need a partnership between quantum and classical computers just for the quantum computers themselves to function reliably. So we need, in particular, we need the classical computers to help us to solve the noise problem with designing better quantum computers and coming up with quantum error correction schemes. And so the way the quantum error correction works is that a classical computer is going to be working in lockstep with the quantum processor, closely integrated. And the classical computer is going to be monitoring for errors on the quantum device and helping to correct those in real time. So building a platform where this is possible is what's going to bring us to this idea that I wanted to define at the beginning of this talk, the Accelerated Quantum Supercomputer. So it looks like a kind of a supercomputing center. And this is how the real quantum computers now and in the future actually are going to be realized. They're not going to stand, a quantum computer isn't something that stands in isolations without classical compute. They're going to look something like this, where the quantum hardware is placed next to the GPUs and CPUs to carry, and the GPUs and CPUs can help carry out things like error correction and real-time calibration and control. But they're as I mentioned earlier, there are several different qubit modalities: trapped ions, neutral atoms. We see some of them depicted here: photonics, superconducting transmon qubits. We don't know which one of these is going to pull ahead of the others, or maybe some of the qubits will be useful for some tasks and others will be more efficient at other problems. So what we're doing at NVIDIA is not locking in on one qubit technology. Rather, we've developed an open source qubit agnostic platform in which we can easily connect our GPUs to different quantum devices and swap in and out the different quantum hardware as needed. And that's kind of our vision, what an accelerated quantum supercomputer is. It's like a supercomputer that's accelerated by also quantum. And CUDA-Q is our platform for helping to orchestrate and program in this hybrid environment. And so just to give you some concrete ideas what I mean by qubit agnostic that might resonate more than the words trapped ion and neutral atom, you may have heard of some of the companies out there working in the quantum space and building their quantum computers. We can work with a lot of these companies and connect our GPUs with them. And these are just some of the platforms in which CUDA-Q is interoperable with these devices. And these all actually can be accessed, or many of them can be accessed through AWS Bracket. So while we're working toward the vision of an accelerated quantum supercomputer, we're actually a way off from it. Fault-tolerant computers aren't here today, but there is a clear path to get to this accelerated quantum supercomputer. So that's sort of the future, and this is where we're at today with noisy experimental qubits. And what we need to do is overcome several roadblocks, and we think that AI supercomputing, another, classical compute, right, is the tool actually that's going to help us to remove these roadblocks that are standing between us today and the future accelerated quantum supercomputer. So some of these roadblocks are that we need better low noise quantum hardware. But even if we get to that point where we can build low noise quantum hardware, they're still going to have noise. They're still going to have errors. And so we actually still need to have error correction. In our classical computers today, we have noise and error correction. We just don't have to think about it because our error correction is really good. Well, in quantum, our noise is really high and our error correction strategies aren't that great. And so we need better error correction strategies out there. And then also, like, even that now or and in the long term, we need better algorithms that maybe are less susceptible to the noise. Maybe they can handle a few errors and still give you some reasonable results. And so coming up with better quantum algorithms and better applications is another area in which we need to improve on. And executing these algorithms, many of them are hybrid. They require GPUs and quantum processors to be connected with a tight interconnect between them. Because if you have a quantum computer talking to a classical computer and they're far apart, you're spending all the time that you may have saved on the compute being accelerated by the quantum computer. You lose that time on communicating between these two devices. And so we want the solving the problem of tight connection between the devices is also another challenge that we have. And so as a community, it's actually our responsibility to ensure that the next generation isn't just aware of these problems that the industry is working on, but that we're training the future industry, the current students today, the students of the future, we're training them so that they can actually address these challenges that everybody is facing in the industry. So let's explore some of these roadblocks to getting to an accelerated quantum supercomputer in more detail. And I'll show you how we can actually build a curriculum to provide the essential preparation for our students to enter the workforce and join the workforce in tackling these problems. So the first area is quantum algorithm and hybrid application development. So coming up with better quantum algorithms. Right now, we're actually leveraging AI to do this. And so one example of this is an application of quantum computing to run molecular simulations for things like drug discovery. So currently with our noisy quantum hardware devices today, the variational quantum algorithms offer some promise for doing these simulations, but they actually suffer from some serious optimization issues. You can think about an algorithm, a variational quantum algorithm as, I want you to kind of picture this in your head. Unfortunately, I don't have an image here on the slide, but you can imagine like a landscape or a surface, maybe a sheet that's sort of been tossed into a room and it's sitting on top of chairs and couches and has highs and lows. And our goal is to find the low point of the landscape, the low point of the sheet that we've sort of tossed in our room that we're kind of investigating. But we don't have a great view of it from above, right? But what quantum computing helps us do is that with a variational quantum algorithm, we imagine that we're a point or like on that surface, on that landscape, and we're moving around the surface and we're trying to keep moving downhill to find a low point. Well, the problem with this approach is that you run into the issue, as any calculus student can tell you, when you're trying to find the minimum, you may run into local minimums and totally miss out on the global minimum. And this approach also is what's called susceptible to the barren plateau problem. And that is as if you have a very flat surface and maybe your minimum is far away, you might get stuck on that really flat part of the surface and never see the minimum. And so this is inherent in this type of problem, and the variational quantum algorithms like fall prey to that barren plateau problem. And so we need, ways to improve this algorithm. And so what we've done is we've actually applied a large language model to build a quantum circuit that's maybe less susceptible to these sort of issues. And so the way that works is analogous to how a large language model works. Instead of building up a sentence word by word, as a large language model does, like ChatGPT, what we're doing here is we're building up a quantum circuit, gate block by gate block, and we want it to satisfy certain properties. So we're using this model to generate new quantum circuits that might perform better than the variational quantum algorithm is on these molecular simulations. And so we've seen some positive improvement or results in this direction. One of the things to note is that in the variational quantum algorithm, it's actually a hybrid algorithm. There's a quantum compute part, and when you get the result out of the quantum computer, you send it through a classical computer to update some parameters and essentially tell the particle that's moving along the surface. I mean, all of this is metaphorical, but to move in a different direction. And so we run the quantum circuit again, maybe moving in a different direction. We get some output about what the landscape looks like in that area. And the classical optimizer gives us new instructions to the quantum computer to move in another direction. And this goes on and on and on until we've converged down to a minimal solution. That can take a lot of time, and you're running the quantum computer quite a bit, and there's a lot of communication back and forth between the quantum computer and the classical computer. What the variational quantum eigensolver algorithm is doing in the situation is getting rid of that loop. And instead, it kind of identifies the space of the landscape where we should search, and we run it just once through the quantum the computer and sample there to get our minimal solution that way. So we've sort of front loaded all of that loop into the training of the model, the AI model. So another example of where AI is playing a role in developing better hybrid algorithms is in collaboration with Yale, and this is to explore the analog of the classical transformer model. So research here are using classical transformer algorithms to generate new molecules, and they also then created a quantum transformer to generate new molecules. And the results show actually that the classical models and the quantum models give different or learn different features. So this suggests that maybe combining classical and quantum models could enhance molecular generation. So even if we've got these better algorithms, and that's as technical as it gets, don't worry, we're going to get less technical now. So even if we have better algorithms, we're limited by the quantum hardware in terms of the noise, the qubit fidelity, and also the scale, the number of qubits that we have in a quantum device. Like I said earlier, today's best quantum processors really can perform only about 100 operations, represented here by these little boxes on the grid, before noise kind of overwhelms the system. So scaling quantum hardware into useful quantum computers requires companies to better understand how to build less noisy qubits. So in order to do that, you really have to understand the noise. So, so that's not saying we want to understand how the quantum computer works, like the inputs and the outputs, but rather we need to kind of dive into the actual physical computer itself and understand how the physical qubits, represented by these spheres here, interact with each other and the environment. Now, some of this interaction is intentional. It's part of the quantum program. We want two qubits to become entangled as part of our quantum algorithm. But there's going to be entanglement that happens sort of by accident in nature. And that's the noise of the system. And we need to understand how that works. And to simulate that noise or the noisy dynamic interactions of qubits, that's computationally intensive, almost prohibitively so. Just to give you an idea, until recently, it would take weeks of classical supercomputer time to run a simulation of a single quantum processing unit, a single quantum computer qubits inside of it and the noise of them. Multiply this by the dozens of different quantum computer designs that you would want to test before putting a product into production or into fabrication. And we're talking about years of it would take years to do all the simulations necessary to design the next quantum computer. But the good news is that together with Google last year, we introduced CUDA-Q Dynamics, and this took the simulation time down from like a year to just 50 minutes to run the design iterations for designing the sort of the next quantum computer that you might test out and build and experiment with physically. So probably that's building better algorithms, building better physical quantum computers. But even if we have better physical quantum computers and algorithms that are less susceptible to noise and converge faster, we still need error correction. That's never going to be going away. And that's probably the biggest challenge standing between today and useful quantum computing. So to help develop better error correction, so we need to develop better error correction strategies. And one of the ways that we're doing this is actually using AI again. And this is where quantum data generation comes in, because I mentioned this sort of AI, right? Right now for the quantum error correction, if we're going to build an AI model to do that or help us with that, we need to train it, right? How do you train? Like, what's the data for training a quantum error correction? You're trying to teach the AI how to recognize noise and fix it, right? So your data is noisy quantum simulations, like on a noisy quantum hardware runs or executions of quantum programs. That means you have to have a lot of quantum computers running and collecting data on it and like recording that data to use as your training. And these models need immense amount of data. You don't have enough quantum computers out there to just, or the time just to spend on generating training data of noisy noisy quantum processor execution. So you can actually use GPUs to create synthetic quantum noisy data. And so being able to generate a lot of synthetic quantum data is also another area where classical compute can come and help. So back to to the problem of error correction, there's a couple of ways which AI can help. One is that just like in building better algorithms for simulating molecules, we can use AI to generate better error correction schemes and algorithms. But that's not the only place. What happens in a error correction scheme is you've got the classical computer watching the quantum computing outputs and processes going on, and it will recognize errors are coming and have happened. And then the classical computer has to send instructions back to the quantum processor to fix those errors before the quantum processor gets on to their next step and those errors propagate. So there's a couple things going on there. One is the fast communication. You need this to be done in real time before the next quantum set of instructions get sent. I mean, that's like sub-microseconds, right? So then the other thing you have to do is you have to actually identify that an error has occurred. That's one thing. The other thing is, how do you fix that error? That's a hard thing to sort through when you're dealing with many, 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 many qubits. It's like an NP hard problem type of thing. So you need fast classical compute to do that, and you need a smart way to find those instruction sets. And so that's where AI can come and help identify patterns really quick and infer from the limited amount of information it's got from the quantum computer, what would be a good instruction to send back to the quantum computer to fix that error. And those are called AI decoders. And like I mentioned earlier, in order to train an AI decoder, you need to have to be able to synthetically generate a ton of noisy circuit executions in order to have that inference model. So just to give you some idea of how fast GPUs can help in this realm is that in order to, for instance, simulate a 35 qubit system and get a whole bunch of noisy data to train the AI, we can get 1 trillion shots in just about 2 hours. And you probably wouldn't have the resources available to do that on a quantum computer and definitely not get it done in that amount of time. So that's just one other way in which classical compute and quantum, you have to have them both. They have to be working together. You can't be doing it in isolation. So synthetic data is one thing. Like, how do you know that synthetic data really looks like what's going on in the quantum hardware and it will work? So what we've done is we've given this synthetic data and this trained AI model, AI decoder, to a quantum computing company, QuEra, and they then were able to refine that trained model with their real data. A smaller amount of it. They didn't need trillions of shots. They just needed a little bit to really fine tune that model for doing error correction on their hardware. And they saw great improvements over their state-of-the-art error decoder. And so this is suggesting that this might be a way for us to move towards practical quantum error correction. And then finally, this idea of a distributed computing environment, a big quantum supercomputer here, where we have lots of different devices, all different types of devices. How do we connect them together in low latency connections? And how do we orchestrate, like, what tasks go to one computer and the other? And, that just how do you program a hybrid device like that? That leads to distributed computing, which CUDA-Q was built from the ground up to do. And just to give you an example of sort of the power, well, I guess maybe, yeah, I want to talk first about why we would need distributed compute. Many of the quantum hardware companies out there, their goal, right, is to build a big quantum computer with a lot of qubits. They're not just building one big device with thousands of qubits. They're building several smaller devices and linking them together. And so how do you take a big problem that might need 1,000 qubits and split that problem up onto devices that only maybe have a couple hundred each? That's a challenge. And if you can do that in an effective way, you actually might speed up things too. So you have to first divide the problem up into smaller pieces. And then if we can run those smaller pieces simultaneously and exploit parallelization, then we can get to a solution faster. So this just kind of represents a quantum problem, or a problem that we might have, is this graph, and we break the graph up into smaller subgraphs. We try to do those subgraph solutions one by one. It takes a long time, but you can see here that if we're able to do those subgraph solutions simultaneously on like 4 different processors, we can get it done much faster. So how to orchestrate all of that is a big problem. The first thing is you've got a big problem, circuit, big graph. You need to break it up into smaller circuits, smaller graphs to try to actually divide that problem up into small pieces that can go on each one of these smaller devices. you can do it naively and you might get garbage results out. Not every problem can be broken up just arbitrarily. You have to be really smart about how you break a big problem up into smaller pieces and solve those smaller pieces independently, because those pieces might depend on each other. And so where there is dependence, you need to make sure you do some post-processing to like fix your solution, and so that your final solution actually makes sense and is what you're aiming for. So we're using actually AI, this is joint work with HPE, to identify if you've got a big problem, how do you break it up in a very clever way? That's where AI comes in. It recognizes how to break up the problem in a smart way so that the post-processing that we get done at the end is minimized, and so that the results that we get at the end are actually accurate as well. And so that's a process called circuit cutting and circuit knitting. So those are just, some of the challenges that we're facing and some of the ways that we are trying to solve these challenges. They're not complete solutions. There's all different kinds of approaches to these challenges as well. These are all active areas of research that the industry is tackling. And I do want to mention that they're not done in isolation either. People are tackling these challenges so that we can come up with an end-to-end workflow. From writing your quantum algorithm that might be novel to running it on machines with really good error correction that happens to be good for the actual physical machine that you're working on and the algorithm that you're trying to run, and then doing the post-processing, et cetera, in a very efficient way. And one example of this is with IonQ and AstraZeneca. We helped to develop an end-to-end workflow on AWS Bracket to simulate a catalytic reaction that led to a 20 times faster solution. And this was a hybrid problem. And the interesting thing here is only the hardest part of the problem was solved on a quantum processor, this beginning part here. The rest of the workflow actually then was moved on to a classical device accelerated by GPUs. And so this result shows how a carefully co-designed quantum classical workflow spanning all of these issues, quantum hardware, error mitigation, classical post-processing, novel algorithms, thinking about these things holistically, that can help us to tackle the toughest molecular simulations and accelerate the drug development. So you may have noticed that many of these examples I've mentioned aren't being done alone. So we're approaching the problems holistically, but we're also doing it too in a holistic kind of ecosystem, right? These collaborations are examples of using AI for quantum computing, and they just represent a small portion of our work. And we're partnering with nearly everyone to advance the technology, from academics to startups to large companies. We're working on problems to improve hardware, software, applications, and all of those together. And we're using GPUs and AI supercomputing, not just for simulation and synthetically generating data, but also and not just on simulating quantum algorithms themselves, but also using GPUs to simulate the physical hardware and to create these AI models that can accelerate and doing the classical post-processing that's necessary. So I've just thrown a lot of technical information at you and laid out kind of a blueprint for the accelerated quantum supercomputer. And so now that we have some idea of what it looks like and what the challenges are, so we know kind of about what its components are, the architecture, and the crucial role of AI and all of that. Now we can start talking about the architects or the builders of that device, right, of that blueprint. These are going to be the students who take this blueprint and construct the next era of innovation. And so what skills do they need in their toolbox? This leads us perfectly into our second question. How do we design an educational model that prepares the next generation of quantum pioneers? So building the educational model is a massive undertaking. A lot of people are working on it, right? But and you may question, like, where do we even begin? Fortunately, people have done this sort of thing before. We're not the first people to create education. Is the most important. Simply, how do you actually teach the stuff? The future of quantum computing is, as I've mentioned many times here and given you countless examples, it's hybrid. It depends on the interplay between classical and quantum hardware. So a purely theoretical approach is just not going to cut it. Talking about quantum computing by itself, working on a quantum computer by itself, it's not going to give the students the skills that they need, because the industry is working with these devices together. The answer, as the slide suggests, is that we have to make it practical. So we need to ground the curriculum in industry relevant problems and create immersive hands-on experiences where the students are working directly with the GPUs and the quantum processing units. And that's the only way to make an abstract concept like scalability feel real. So if the curriculum must be practical and industry relevant, the next logical question is how can we possibly teach that? And the challenge is a combination of a limited pool of trained faculty and the fast pace of innovation in this field. So the tools, the platforms, and even the most effective techniques in the space are evolving quarterly, not maybe even weekly, right? Not semesterly. So no textbook or traditional curriculum can really keep up with the field that is being redefined in real time by the industry. So this creates a natural gap between the foundational knowledge taught in academia and the state-of-the-art practices that are actually essential in the workplace. So to bridge this gap, partnerships between industry and academia are not just beneficial, they're essential. Right? They provide a direct channel to ensure that the curriculum, the computational resources, and the projects remain current and relevant. So our next challenge is defining who learns. If we only teach quantum to physicists and computer scientists, we will miss its whole purpose. Just like with high performance computing, the most compelling problems come from other domains. And this means we need to actively expand our quantum education beyond its traditional departments and integrate it across the entire STEM curriculum. The roadmap for this is clear. We can follow the model of computer science, which has, over the last 2 decades, has successfully embedded computational skills into biology, chemistry, and engineering, all the STEM disciplines. The immediate goal is to bring integrating relevant quantum computing examples and concepts into these non-quantum courses, making them accessible to a broader audience. And finally, when we design a curriculum like this, a competency-based approach is effective because it focuses on what leads to success at work, if we're talking about workforce development, right? Knowledge, skills, and dispositions. But there's a fundamental flaw in how quantum education is often approached. The conversation tends to focus on the quantum knowledge and skills in isolation, treating it as a standalone subject. This is a major oversight because in the real world, quantum is inseparable from HPC and AI systems that power it. Therefore, a modern curriculum has got to redefine knowledge and skills to be an integrated blend of HPC, quantum, and as we saw, AI. But even if the technical integration is achieved, it only solves part of the problem because that's just the knowledge and skills. The third critical component is often overlooked, and that's the dispositions, the mindset, the factors that define a student's success and beyond the technical skills, right? And so we can ask what mindset is most essential for students to succeed with accelerated quantum supercomputing. So let's break down this question on the slide. We have a great starting point from the existing competency frameworks that are out there for computing education. And the list here gives you some of them. We see proactive, collaborative, meticulous, etc. Naturally, in a new field like quantum, being adaptive and inventive is absolutely critical. And since it's fast changing like that, like being able to just understand that what you learned last week might not be relevant this week, right? That mindset, it could really help you. But is that enough? I argue no. The mindsets needed for accelerating quantum computing is fundamentally different than just those that are needed for succeeding in an emergent technology like HPC or AI were in the past. It's not an extension of how we think classically. Quantum isn't. So it's a leap into like a counterintuitive, probabilistic way of thinking. And so that means we have to have competencies and dispositions and mindsets, right? Or we have to have dispositions and mindsets that can deal with this counterintuitive way of thinking. So things like interdisciplinary thinking and a constant awareness between the gap between textbook examples and industry application, and that the industry is still working on these problems for a real application, right? Just that awareness is key. And of course, then being able to think statistically and being able to evaluate multiple solutions because you're going to have multiple solutions, right, in a quantum algorithm. So these are the skills that will equip a student. These are the dispositions that will equip a student for the convergence of high performance computing, AI, and quantum computing. Yeah, that's needed for that defines essentially an accelerated quantum supercomputer. So let's work through like just an example of building up a competency with this in mind for quantum computing. So first, right, it had to be industry relevant. So let's look at an example of formulating and solving a financial portfolio optimization problem. Definitely industry relevant. We can ask what kind of knowledge is necessary to solve this problem. And so we need to translate that portfolio optimization problem, those investment scenarios, into constraints and in quantum models, a QUBO model, not quantum model, a quadratic unconstrained binary optimization model, which we can solve classically. And it's important to know the classical solution to that. But also we can solve it with quantum algorithms, like the fundamental ones that you see often noted, QAOA or quantum annealing. And maybe thinking about how, if this is going to be an industry relevant problem, if you can solve this problem for a 10 qubit or 20 qubit, it's probably can be done classically, and you probably don't need quantum computing for it, right? So scaling this up is really important for a problem to be industry relevant. So we have to address that in the classroom. So how do you scale up QAOA or annealing or other approaches from the quantum space so that we can actually start to think about solving these industry relevant problems, not the toy problem? Well, that's going to require some skills too. You need to be able to formulate and solve the problems, right? By able to translate this application into like a quantum algorithm and implement, the foundational algorithms and approaches that you're learning about in quantum computing. But you also need to evaluate those solutions, compare them to classical results, and to some of the industry like cutting edge results that are out there, like for instance, JP Morgan Chase and Inflection have come up with the QCHOP algorithm, which is a proprietary method, but we can still learn from it, that improves QAOA, right? And so this actually addresses that disposition of the awareness of the research to application gap. The being able to compare those textbook examples to this involves critical evaluation, right, of the results that you're getting. And even in this space, there's other ways you can evaluate and critique the problem, right? You can look at the critical trade-off there is between sampling and solution quality, right? So being pragmatic about your problem solving, that you're not just going to run the algorithm as stated with the parameters given by your professor type of thing and call it the end of the day. You got to think like, where did these parameters come from? Why did I take 1,000 shots? Why did I take 10,000 shots? Why was my circuit this deep versus being more shallow for QAOA? So that's pragmatic problem solving can be captured. That disposition can be fostered with students by looking at these and challenging them to answer questions like that. And finally, systems thinking. Like if we want to actually solve really large scale financial problems, it's not done in isolation. Those problems sort of depend on other things that might be solved classically. And just so how does this fit in the big ecosystem? How do classical compute and quantum compute come together? So that's a detailed look of like one competency, but it's built on a foundational principle that the future of computing is hybrid. Breakthroughs won't come from quantum alone. They're going to require deep integration of quantum and AI. And preparing students for this reality requires a sort of holistic approach. So my message here is that if we want our students to be ready for the future, we need to build our curriculum around a complete framework. As the slide summarize, we have to address the 4 questions, right? How we teach, we're going to teach with practical hands-on industry relevant problems. Who does the teaching? A partnership actually between academia and industry to stay current. Who learns? Well, a broad audience of domain experts across all of STEM. I mean, the people doing the financial portfolio problems, those are not going to be necessarily in the physics classroom. They're going to be possibly, in the finance department. So let's hit those students where they're at with the knowledge that they need to understand the basics of that quantum algorithm and how it might apply to their industry. And then finally, what we teach, an integrated approach to HPC, AI, and quantum, and emphasizing the dispositions along the way with that competency framework. So we've actually addressed these 4 challenges together. We're working on it. We're not, it's a big problem, right? to create an educational yeah, so we're not, rather, I guess, back up a step. I guess what I'm saying that this is kind of a framework that we can follow, and we're building towards this, putting some of these tools into practice. And we've teamed up with several universities to work on this approach, to develop curriculum material, to prepare the students for the accelerated quantum supercomputer and to get there as well. And these are just a small sampling of some of the universities we're working with. And the program is called CUDA-Q Academic. It's a curriculum designed to create a clear path for students and by building on all of our content around solving practical industry problems. Those are the major challenges that we're facing today that we can kind of all agree on. These are big challenges. And so we've mapped our curriculum to these challenges. So for instance, students interested in applications like in finance, we've got a portfolio optimization module, like that's where the competency that I just went through comes from. So that grounds that quantum algorithms that they're learning about in a real world business problem. So physicists and engineers, though, might be more focused on the hardware and large scale systems. Our curriculum offers hands-on learning models such as Dynamics tutorial that teaches a simulation of open quantum systems. How do you simulate those physical qubits to design the next best quantum hardware? So we teach students to use that Dynamics API. And building out that kind of education, though, too, requires a community collaboration, between, then that becomes more essential as we get really specialized with designing a quantum computer, right? So, for example, professors at the University of Copenhagen and the Technical University of Denmark are not just building a new course using CUDA-Q and our tools, our open source tools. They're also co-developing new tutorials and contributing them back to CUDA-Q Academic for the whole community to use. So another set of notebooks we have regards quantum error correction, and that's a perfect example of integrating quantum and AI. So it takes students from the basics of quantum error correction all the way to implementing an AI-powered decoder that I mentioned earlier in the talk. So they learn how to improve the speed and accuracy of that decoding with AI. And finally, for computer scientists tackling the challenge of scaling this out in distributed computing, we have a module on distributed workflows that uses techniques like circuit cutting to prepare them for the future of large-scale hybrid computing. So as you can see, this isn't just a set of tools we're providing. It's a kind of an ecosystem built with the community, the professors, the universities that are using this material, and also contributing back to the material that we have on our GitHub. And it's connecting foundational learning to real-world challenges. So we've covered the technology and the framework for education, and that brings us to the final and perhaps the most important question: what's next for you? So to answer that, I want to make sure you leave today not just with information, but with a toolkit. So let's look at some of the resources you can use to put these ideas into practice. CUDA-Q Academic Curriculum, that's a perfect starting point for structured learning. So starts with a quick start to quantum computing, like where you can learn the definition of a qubit and move on from there and get your first Hello World program, a variational quantum algorithm, actually, program in about 4 hours. And so that can get you started if you're new. But depending on how you like to learn and what you need to learn, we've got blogs for the latest updates and real world applications. I've got some information here on our documentation page. If you want to deep dive into the documentation to get into the technical details and maybe even contribute back to the CUDA-Q open source project and get a line on your resume for that. And that'd be one way of learning by doing, by contributing back to GitHub. And everything you need to get started and stay engaged is kind of like right here on the slide, so take a screenshot. We covered a lot today, from the core technology of qubits to accelerated quantum supercomputers to a framework for education. But this is really just the beginning of a conversation of how to prepare the workforce for the future of quantum, because the future is also changing too. This is a starting point with the resources on the slide, and I'm excited to see what you guys all discover. So thanks. I'll go ahead and leave the slide up as we open it up.